Hey, good afternoon, everyone. Welcome to the second webinar of the MAP program's 2015. Sorry, I've got to share my desktop. The second webinar of the MAP program's 2015-2016 webinar series. My name is Heather Archambault, and I'm a program manager in the MAP program of the Climate Program Office. Dan Barry and I will be taking turns hosting the MAP webinar this season. Our webinar today is on transitioning prediction and social science research into NOAA Operations, and includes presentations on 3 diverse projects supported by the NOAA Office of Oceanic and Atmospheric Research and the National Weather Service. Today's webinar, which is co-sponsored by the Office of Weather and Air Quality in OAR and the Office of Science and Technology Integration, the National Weather Service, or NWS, is designed to highlight the diversity of transition work being done across NOAA and let the agency's strong emphasis on R2O and R2A type projects. And this is an effort that is being championed by our chief scientist, Dr. Rick Spinrad. So today we have 3 15-minute presentations scheduled, and there's time for questions after each. The phone lines will be muted during the presentations, but if you'd like to ask a question, you can virtually raise your hand in WebEx, and we'll unmute your phone. You can also type your questions into the WebEx chat box. Okay, so with that, I'd like to introduce our first speaker, Jim Wilczak, who is a research meteorologist at Esmol's Physical Sciences Division in Boulder. Jim's research that he'll be discussing today concerns the prediction of fine particulate matter, which is an air quality hazard responsible for tens of thousands of premature deaths in the United States each year. His research is supported by both STI and OAC. Okay, Jim, are you ready for me to try transferring controls to you?
Yes, if you want me to try.
Yes, we will give it another shot here. So I'm transferring over now.
Okay, are you able to see the slides, Heather?
Not yet. Did you click on share? Did you go to the quick start tab and then share your desktop?
Well, I don't have that up on my screen again now.
Okay, well, Jim, maybe
okay, let's do, here we go, quick start.
Okay.
Okay, let's try again.
Oh, great. Nice. Now it works. Okay, perfect. So go ahead, Jim.
Okay, great. Thank you very much, Heather. So as she said, I'm Jim Wilczak from NOAA's Earth System Research Lab, and I'll be describing a research to operations effort to improve operational NCEP forecasts of PM 2.5. And the main groups that have been working on this are shown here. On the first line, a group from ESRO, and then on the second line, a group from National Weather Service, in particular Jianping Huang, who has helped out a lot on this presentation, and then also Luca Delmonica from NCAR. So let's see if oops. I'm not sure what you see, Heather. I see a blank screen here now.
As do we. Would you like me to step through for you?
Sure. Let's see. I don't.
Try hitting the space bar again, Jim.
Okay, does that work?
Yeah, I just took control back, but I'll give it back to you. Okay. Just 1 second. You'll just need to share your screen again. Okay. So you're back in that quick start tab?
Right.
Great, yeah. Excellent, okay.
Okay, sorry for the confusion here. So, what is PM 2.5 and why is it important? So PM 2.5 stands for particulate matter that's smaller than 2.5 microns in diameter. And it's important because, as Heather mentioned, the health impacts, there's literally been thousands of epidemiological studies that have demonstrated that there are anywhere from between 65,000 to as many as perhaps 200,000 premature deaths in the U.S. each year associated with PM 2.5. So why is it difficult to forecast PM 2.5 accurately? Well, forecasting PM has all the traditional problems of forecasting the weather, except with several added complications. The first is that there are very few observations available to initialize the model. Second, there's a really big uncertainty in the emissions. Also, PM 2.5 can be created in the atmosphere from chemical reactions that involve other gaseous pollutants, and there's some uncertainty in these chemical reactions. And then finally, you have the weather. The concentration of PM 2.5, it's going to depend on things like turbulent mixing, the depth of the boundary layer, transport involving the wind speed and the direction. And so when you add all of these uncertainties together, you have a very complicated modeling system. And considering all of the uncertainties, I actually find it pretty amazing that PM forecast models have much skill at all. Okay, Heather, how do I move to the next slide? It's not responding.
Did you try clicking your mouse? Oh, there you go.
Here we go. I guess there's a long delay. Okay. So the centerpiece of the NCEP forecast system is the Community Multi-Scale Air Quality Modeling System, or CMAC. It's a regional chemical model, and the domain is shown in the black lines in the figure at the bottom. And it's driven by the North American Mesoscale Meteorological Model, the NAM. The emissions inventory come from the NEI, National Emissions Inventory. And then in addition to that, there are forest fire emissions that come from NESDIS satellites, together with U.S. Forest Service emission estimates. And then global chemical prediction models are used to provide lateral boundary conditions, but they really are used only as monthly mean values for the lateral boundary conditions. But they also provide daily dust estimates, and that can be pretty important at certain times of the year. And initial conditions for the forecast just come from the previous forecast. There's no actual chemical data that is assimilated into the model itself. PM 2.5 verification occurs at about 600 EPA AirNow sites, shown in the figure at the bottom. Those that have more than 80% of the data over a one-year period are shown in blue in there. And just as a point of reference, the EPA has standards that they apply to these different areas in the country, and those standards at which you have a violation are 15 micrograms per cubic meter as an annual average, or 35 micrograms per cubic meter at any particular individual site. Okay, and so how is the CMAC model performed? So this figure shows the monthly mean PM 2.5 CMAC biases for a 7-year period from January of 2009 to July of 2015. And the different color lines indicate the biases for 6 different regions of the country. And you can see that the biases have a very significant seasonal variation, being positive or having an overprediction in the winter months, and negative, which is the model underprediction in the summer months. The magnitude of the winter bias has generally improved over time, but the summer bias really has remained almost constant over this 7-year period. I should also point out that the magnitude of these biases are a significant fraction of those EPA standards of 15 and 35 that I'd mentioned previously. So despite the large monthly biases of 5 to 10 micrograms per cubic meter, historically there have been no routine post-processing of the model forecast to remove these biases. In contrast, weather forecasts, of course, which have considerably more skill than the PM forecast, have had routine and generally have routine post-processing using MOS-type techniques. So applying some type of post-processing to PM 2.5 forecasts is really an obvious route for trying to improve those forecasts. So the main technique that we have been developing and using for this is an analog bias correction technique, and it's the method is illustrated in this figure here. And we show it here for an ensemble of really only two forecast analogs. So the black curve in the top panel is a time series that's predicted by the model over an 8-day period, and the red curve is the corresponding set of the observations. The same hour of the day is considered within each day, and the data on the right side of the dashed line at t equals 0 represents the new forecast, while the data to the left represents the previous 7 one-day forecasts. And as shown in the top panel, the analog search technique searches for the previous forecasts at the same lead time that are similar to the current forecast, which is shown as the blue star. And where the similar forecasts are circled in black, and then it reorders the time series with the closest analog directly preceding the new forecast, and then the second closest analog being next, and that's shown in the bottom panel. So the observations in red corresponding to the two best analog forecasts are then weighted by how closely they resemble the current forecast, and then their weighted sum provides the corrected forecast estimate, which we refer to as AN for analog. And although this schematic figure shows only two analogs, in practice you can use any number of analogs. So the initial portion of this research work was done on a one-year CMAC dataset from 2010, and I'll show a few figures from that. We not only investigated analog bias corrections, but also combinations of the analog technique with Kalman filtering. And these figures show the sensitivity of the post-processing to the meteorological search variables that are used. And the results are shown just for 1 month here from November 2010. And the left panel is for the mean absolute error, and the right panel is for the correlation. The red bars show first the raw CMAC forecast, and then several simple corrections that do not use analog. And you'll note, for example, that persistence, which just simply says that today's forecast of PM at 3 p.m. is going to be exactly the same as it was observed yesterday at 3 p.m., actually has a lower MAE than the CMAC model. So it shows that there's a lot of room for improvement here. And the color bars on the more towards the right of the figure show the sensitivity of the analog results to the search variables chosen. And the analogs, as well as a combination of analogs and Kalman filtering, are shown. And the best results come when we use PM, temperature, wind speed, and wind direction for our search variables. And of the three schemes shown here, analog is the one that's currently being implemented at NCEP, and so that will be what I'll talk about as we go forward here. So in this figure, we show on the left side is the total RMSE in the top panel, and the unsystematic component of that RMSE is in the middle panel, and then the systematic component is in the bottom panel. And as you can see in the bottom panel, the analog scheme does a pretty good job of removing almost all of the systematic or the pure bias component, which is, pretty much expected. However, the middle panel also shows that the analog post-processing is capable of reducing the unsystematic or the random component of the RMSE by about 30%. The right figure shows a histogram of the forecast error with the red curve for the raw CMAC model and the blue curve for the analog corrected forecast. The raw model errors are asymmetrical, skewed towards large positive model errors. But in contrast, the analog corrected forecasts are symmetrical, centered around 0, and have a much narrower distribution, all of which are things that you would want to have from the forecast. So here we see the hourly time series of CONUS average PM 2.5, again for the month of November. For the CMAC forecast in red, the observations in black, and the analog corrected forecast in blue. The CMAC and the analog forecasts are used at the 570 locations where we have the observed PM. And CMAC is seen to predict too large of PM values on the red curve by quite a bit. However, this degree of overprediction varies considerably from close to like 10 micrograms per cubic meter on the 12th of November to only about 1 microgram per cubic meter on the 24th. So there's a lot of variability in the skill of the model over time. However, in contrast, the analog corrected forecasts never differ more than about 3 micrograms per cubic meter from the observations, and they generally follow the day-to-day trends in the PM. So those previous results were shown just for 1 month of the forecast, and here we see the results for an entire year, MAE on the top and correlation on the bottom. And we see that the results are very similar for all months of the year, with the MAE in the top panel reduced by about 30%, and the correlation improved by about 20% from the analog forecast compared to the raw CMAC model. The model corrections that I've discussed so far are for individual point locations where we have a PM 2.5 monitor collecting observations. However, to be really useful for dissemination to the public, the forecasts have to be able to be provided as a graphical image over the entire forecast model domain, and this requires spreading or interpolation of the model forecast corrections from the observation locations to each of the model grid point locations. And so what I'll show next is a method that has been developed for spreading of the model correction values. We define first the forecast model bias at each site location K to be the difference between the analog forecast and the raw CMAC forecast, and then we spread this difference across the entire model domain, and then we add this spread bias correction to the raw forecast at each model grid point. So the spreading method that we use is an iterative objective analysis technique, and it starts by drawing a very large circle of radius r around each model grid point, and then calculates the mean forecast bias of all of the observation sites within that circle that are weighted by the distance d to the model grid point. And the grid point bias, G bias, starts off as being 0, and then it increases in magnitude as the process is repeated progressively for smaller and smaller circles, going from 2,000 kilometers down to 15. And so the three figures at the bottom show how progressively more detail is added to the forecasted model bias correction as the radius of influence keeps shrinking. So now what I'll show is a series of slides provided by NCEP from Jianping Huang, who's been helping us, been doing the implementation actually of this technique on the NCEP computers, and the results are from a demonstration test that is from 2015, so using much more recent observations and forecast models. And first we're going to show results from a winter month from January of 2015. Each of the panels here have 4 lines. The black is the observed PM. The solid blue is the CMAC model being run operationally at this time. The dash blue is a parallel version being run offline with various model improvements that were being tested. And then finally the red line is the analog method that's applied to the parallel forecasts. And these results are divided into the eastern U.S. on the left side and the western U.S. on the right side. And the top 2 panels show the spatially and monthly average mean diurnal cycle as a function of the 48 forecast hours. And in the top left for the eastern U.S., the operational forecasts in the solid blue, you can see they have a significant positive bias, which has been reduced somewhat in the parallel version. The analog bias-corrected forecasts in red follow the observed diurnal variation very closely. And then in the top right for the western U.S., the operational forecasts were biased high again, whereas curiously now, or interestingly, the parallel forecasts are actually now biased low, but the analog corrected forecasts followed the observed diurnal cycle fairly well, although not quite as well as in the eastern U.S. And then the bottom two panels show the day-to-day variation in PM over the course of the month at a single forecast time valid at 04 UTC. In both the eastern U.S. and western U.S., the analog corrected forecasts have smaller bias than the raw models and generally follow the evolving trends over the month, although they do tend to smooth out some of the day-to-day forecast variability. Slide 12 here continues this evaluation for the winter month, with the top two panels showing the forecast maps for a particular day and hour. The circles show the observation locations, with colors within the circles showing the observed concentrations. And the left panel is for the raw CMAC model, and the right panel is for the analog. And one can see that the gridded forecasts shown in the background colors have been reduced on the right and now agree more closely with the observations. Importantly, the corrected forecast map also just has kind of a general, similar appearance as does the original forecast, which makes it easy to disseminate. The bottom two panels show the RMSE for the eastern and western U.S., and again, you can see the analog corrected forecasts in red have considerably lower RMSE than either the operational or the parallel forecasts. And here we see similar results for the summer months, and again, you can see how the red curves of showing the bias-corrected forecasts follow the observed diurnal cycle much better in the top two panels, and in the bottom two panels, you can see how they follow the daily variation of observed PM 2.5, and generally follow the kind of day-to-day trends. So in the interest of time, I'll skip this next slide and go straight to what our current status is and what our future plans are. So the analog scheme's been in developmental testing at NCEP for a number of months now, and it's had a limited dissemination of its results to a select users and evaluation group. Pending the evaluation results from this test, the analog bias correction is planned to be released to the public sometime later in this fiscal year. And then finally, in terms of the research, where we're going in the future, we'll be doing not only the analog, but also the Kalman filter analog implementation, testing that. We'll be doing the parallelization of the post-processing code so it can run more quickly at NCEP. We'll be doing a regional optimization of the analog searches, and then we hope to also be able to develop new techniques to better treat forest fire episodes. So I'll stop there. And Heather, I'll turn it back to you. Heather, I'm not sure if you're on the line, but I'm not hearing anything.
Okay. Now it says that I'm the presenter. I'm just.
Hello?
If I can share my. Hello?
Hello, this is Jim.
This is Nat. It says it's transferred to me as presenter. Do not see any share screen sign.
Something there.
Oh, shoot, okay. Sorry about that. We hit mute accidentally here. So Nat, go ahead whenever you're ready.
Okay, I don't see a share screen.
So do you see the WebEx browser?
Yeah, I see.
Are you in the quick start window?
Oh, quick start. Okay, gotcha. Okay. Okay, so I guess you can see.
Yep, great, thanks.
Okay, great. So, so thank you, everyone. Dan Harnos and I are going to be talking about the operational transition of combined ENSO, MJO, and trend influences on temperature and precipitation for weeks 3 and 4. Just like to acknowledge our team, Steve Baxter, Stephen Feldstein, Josh Fang, Michelle LaRue, Strength Shea. Okay, and so the National Weather Service has a suite of products that are designed for seamless weather and climate prediction, extending all the way at the shortest time scales of minutes to hours to days to about a week to 2 weeks, and then to a monthly and seasonal outlooks. But currently there's a gap between the 8 to 14-day monthly outlooks in weeks 3 and 4. However, the NOAA Climate Prediction Center is currently issuing these experimental week 3 and 4 outlooks. You can find them at this website here. And if these become fully operational, that would help to complete this framework for seamless weather and climate prediction. These outlooks are given in the standard probabilistic format, so probabilities of above average, below average temperature, probabilities of above average and below average precipitation. But it's very challenging to issue skillful forecasts at these lead times. So some key questions are, what are the sources of skill for lead times of 3 to 4 weeks? And then how do we translate that knowledge into operational forecast guidance? Well, there have been many studies that indicating that the tropics are a key source of extended range mid-latitude predictability, and specifically the relationships with the El Nino Southern Oscillation, or ENSO, and the Madden-Julian Oscillation, or MJO, hold promise for weeks 3 and 4. And here's just an example from a study Riddle et al. In 2013. On the top left, I'm showing a 500 millibar height cluster pattern. This is just showing a positive PLA-like wave train over the Pacific North American region, a negative NAO-like pattern over the North Atlantic. And associated with this particular pattern, this is one of 7 patterns identified. There's tend to have below average temperatures over the eastern U.S. in the wintertime, above average temperatures over the western U.S. And what this shows on the right is that the MJO has a significant influence on the frequency of occurrence of this particular pattern, for lead times of about 10 to 25 days. So the x-axis here is the days after MJO phase occurrence, and then each of these panels represents the 8 Wheeler-Hendon MJO phases. And these bars are the anomalous frequency of occurrence of this pattern. And the filled bars are statistically significant anomalous frequencies. And what you can see, for example, about 10 to 25 days after the MJOs in phases 5 and 6, you have this significant anomalous positive frequency of occurrence of this particular cluster pattern. So again, it's suggesting that MJO is potentially useful for these longer lead times. And so how do we transition the gains from our research into an operational forecast tool? And by our research, I'm talking about the research community at large, not just our group. But one thing our group did do is we generated the wintertime North American temperature forecast for weeks 3 and 4 based on a very simple way, based on empirical relationships with the MJO, ENSO, and the linear trend. And this is described in a paper in 2014. Just to illustrate this schematically, so on the left here, I'm showing a hypothetical climatological temperature anomaly distribution at some location. So we would have a 33% and a third probability of temperatures being the upper tercile, 33 and a third % probability of temperatures being the lower tercile. But then for a particular initial phase of the MJO and ENSO, we calculate the mean anomaly for weeks 3 and 4, and we also add the linear trend, and that gives us this mu sub Tg. We also calculate the standard deviation associated with this initial phase. Then we generate a new temperature anomaly distribution, assuming a Gaussian distribution shown as such. And with this new distribution, we calculate the probability of temperature being in the upper tercile, shaded in red, probability of temperature in the lower tercile, shaded in blue. So this would be a hypothetical case. It's enhanced probability of above average temperatures. And we generate a forecast in this way for all North American grid points and for years 1980 to 2013. So it's a simple way, method, but it's transparent. So the forecaster can understand, why he or she sees the relationships, why he or she sees the forecast based on the known relationships in the literature. And it translates research into practical guidance for the forecaster. So it captures the basic relationships that exist in the literature and puts it in a format that can be directly applied to the forecast. And as we'll show, it does produce skillful forecasts at times. And so for some initial states of the MJO and ENSO, the skill scores of these week 3 and 4 temperature forecasts from this empirical model are substantially higher than the typical skill scores we see from dynamical models. Here's an example of a week 3 forecast initial phase of La Nina and MJO phase 8. So on the left here, I'm showing the forecast, and this is in the standard CPC format. So cold colors enhance probabilities of below average temperature, warm colors enhance probability of above average temperature. The middle panel here are the mean Heike skill scores. So values greater than 0 show skill relative to a random forecast. Stippling represents statistically significant skill scores. And you can see, so the broad areas with significant skill. Again, these values are higher than typical values that we see from the dynamical forecast models. And on the right panel, this is showing the mid-tropospheric anomaly pattern associated with this forecast. So these are geopotential height anomaly. And here are just a couple other examples. Week 3 forecast, El Nino MJO phase 2. You could see week 4 forecast, neutral ENSO MJO phase 6. And generally you see, as we might expect, where we have the strongest temperature signal, we tend to have the strongest skill scores and broad areas that are with statistically significant skill. And now for the rest of the talk, I'm going to turn it over to Dan.
Thanks, Nat.
Yep.
Are you guys able to view my slides?
I can see them.
Great.
All right, thanks. So Nat did a lot of the heavy lifting there in terms of getting the proof of concept together, while my role with this project was to get the operational transition underway here at CPC to get this into operations in advance of our first week 3-4 forecast in September of this year. So first, some of just the nitty-gritty details here. Nat's initial research was only for December through March, so we had to transition that obviously to do all seasons instead. So we have 12 3-month running periods instead of the 1 4-month period that Nat looked at. Also, Nat was using the error interim reanalysis, and we had to instead use a couple different data sets that were laid out here as standard data sets for all CPC statistical tools for week 3-4. For temperature, we have the CPC 2-meter temperature data set, Janowak et al. And then we also use the CPC unified gauge-based analysis by Ping Shi et al. For 2-meter temperature, that data set's just daily max and minimum temperature, and we take them average to get the daily temperature and use that relative to climatology for an anomaly. For the gauge-based analysis, we have accumulated daily precipitation with that. Due to the assumptions with the PDFs that Nat showed earlier, we assume that they're normal. Precipitation we know is not normally distributed. So to account for that, we take a fourth route, as suggested by a coworker here at CPC, Emily Becker, in order to increase the normality of the distribution. Also with Nat's sample forecasts that he showed you, those were in a 3-class forecast, which was the typical standard here at CPC. But since the week 3-4 product is experimental, we're trying something new and looking at a 2-class forecast. So instead of breaking things down into terciles with below normal, near normal, and above normal probabilities, instead we just have above and below normal probability relative to the median instead of the terciles. And also with Nat's work, he was showing individual weeks 3 and weeks 4 separately, while instead the official CPC products combine weeks 3 and 4. So the graphics and work that I'm going to show you are just for that alone. So the first question we had is, NAT's work was just for wintertime temperature, DJFM, but we wanted to see how is skill for precipitation and also for other times of year. So just initially here is the weeks 3 and 4 combined Heidecke skill score for the combined effects of ENSO, MJO, and trend. The top row is 2-meter temperature, the bottom row is precipitation, while the left column is wintertime, and the right column is summertime, June through August. So DJF, like Nat showed, largely skillful for temperature, as we kind of saw earlier. Precipitation, though, less skillful in general, but we still have a broad region of above average skill where we're doing better than random chance for the Intermountain West and the southern Great Plains here. Also some in the southern portion of Alaska. But then we get to summertime here, and temperature, we're still seeing some skill, even though our teleconnection patterns aren't as strong this time of year, with this broad region of high skill extending from the Pacific Northwest down the West Coast and across the southern tier of the U.S., and also a little bit of skill here in New England. In terms of summertime precipitation, a little bit here on the West Coast and again across the southern tier. Precipitation signal much spottier than temperature signals we'd kind of expect given the nature of precipitation itself. But as Nat mentioned, the skill tends to go kind of up and down depending upon the base state of where we are in relation to the Madden-Julian Oscillation and El Nino Southern Oscillation. So at the top here is just an example of the Heidecke skill score coverage for 2-meter temperature for June through August during weeks 3 and 4 with an El Nino base state between 25 and 50 north, which is approximately the lower 48 portion of the U.S. And the x-axis here corresponds to the MJO phase that we're in for the base state, phases 1 through 8, and then a weak MJO. And the y-axis is the percent coverage that the 25 through 50 north region is covered by at least 0 Heidecke skill score with the green line, Heidecke skill score of 10 in orange, and then 20 in purple. So we can see with this plot, there's embedded periods of higher or lower skills that are dependent upon that background climate state. MJO phases 4 and 5 doing better here, while 2 and 7 stand out as poor phases in this setup. You will note, too, that even without an MJO signal, just with El Nino here, we still have some skillful forecasts with our statistical tool here. Even without El Nino, just with a neutral base state, we also still get some skill here with the tool, as we don't have to have that active background state due to the nonlinearity of ENSO, and we also have that trend component, which helps us bump up our skill somewhat. But MJO and ENSO still are big drivers in terms of what our forecast is going to be. We're something like this here at the bottom left, which is the Heidecke skill map for phase 2, JJA, where we see there's only really skill across the southern portion of the U.S., a little bit here in New England, or something like phase 4 here, where we have a skillful forecast of reasonably high skill, talking 30 to 40 Heidecke skill scores, which are very solid for pretty much the entirety of the U.S. here, other than this little gap here in the southeast and a little bit here in the Rockies and mountainous portion of the west. So there's still a lot of potential skill here with this tool when we transitioned it from outside of solely temperature and the wintertime season. So I set about working to get through all the processing for this to get this available to the CPC forecasters. And what we've been doing here is a dry run of the forecast before we went live on September 15th of this year. So at the top left here is one of the dry run forecasts. This was made on June 19th. The blue regions signify below normal temperatures, the red are above. This is a 3-class forecast, so there are some regions in here where equal chances or kind of a near normal could be expected. With the forecast for above normal temperatures in Alaska, Pacific Northwest, and the Southeast, and cold stretching from New England back down to the Southwest. At this time, our MJO and ENSO and trend tool was not available to the forecaster, but the output for this base state with El Nino and MJO in phase 4 at this time is shown here in the middle on the left. And the tool here would project above normal temperature here in the northwestern portion of North America, generally cold throughout the central and southern portion of the U.S., warm over here in Florida, which is largely similar here to the forecast that was issued, even though our tool was not made. So it's good for us to see the consistency between the patterns put out with the forecasters who were relying solely on dynamical models at this point in time versus our statistical tool. The Heidecke skill score map is down here for our tool, and if you remember that plot in the last slide with the line graph, phase 4 with El Nino, typically one of our more skillful time periods, which is reflected here. We didn't have a verification for this point in time, but it's down here on the right, just pulled from Ezral's page. So this isn't the tercile, but this is instead the temperature anomaly here. And we see that this forecast verified reasonably well where there was warmth across the northwest and into Alaska, southeast portion as well, and then this cold stretching generally to the Great Lakes back into the southwest, which is reflected both in the dynamical dry run forecast and then the statistical model here. So this was encouraging for us here at CPC as we developed the tool and got this into operations. The same forecast here for precipitation, less coverage on the map with above normal probabilities here across the Rockies and in the northern and central portions of the plains. Below normal precipitation, drier conditions favored across the southeastern portion of the country down into the Texas, southern portion of Texas. Our statistical tool, again, was not used in making this forecast, but there is some differences here in terms of the coverage with above normal precipitation favored across the south, dryness across the north and central, and but this moisture across the west, increased precipitation is consistent here. In terms of how things verified, there are some discrepancies. The dryness that was favored by the dynamical model forecast across the southeast did verify. There's also dryness across the northern tier, which was here in the statistical model, but not picked up on by the forecasters, while the above normal precipitation across the west and the central plains really didn't pan out for the dynamical models, but the statistical model did have a hint of it across the northern and central plains. So again, statistical forecast tool versus the dynamical only model forecast that the forecaster made at this point are both pretty comparable. But we need to have this statistical tool involved to have a kind of additional perspective for the forecasting team here. So quickly, I want to talk now about the actual forecasting procedure here, because this played a role with how we went about R2O and some ways that the forecast team fed back on our work in an O2R sense. So our forecasting process, there's a team of about 10 of us here at CPC who are involved in doing the forecast. We have one lead, and we meet once a week on Friday morning. We have a consensus discussion where we go about looking at our forecasting tools and developing the final forecast product, our two maps, and we have a discussion accompanying that. So I mentioned earlier we had dynamical tools. These are all bias corrected, and we have the CFS, the European, and the JMA Japanese models here. With this, we look at the 200 and 500 millibar geopotential heights to get an idea of the general circulation pattern, looking for consistency or differences between the models. We also have bias-corrected temperature and precipitation anomalies, and then temperature and precipitation probabilities, depending on what the ensemble members for each of the three dynamical models are putting out. So the geopotential stuff shown here at the top right, anomalies at the bottom left, and the probabilities at the bottom right, one example all from the CFS. In terms of statistical tools, we have our ENSO and MJO phase model that Nat and I have been discussing here. With the forecasting group, there's two of us that are involved with the development of the ENSO and MJO forecast phase model. Both myself and Steve Baxter, we have been involved in the forecast process for this and going to the forecast discussions every week. This has been extremely helpful for us and the forecasting team as we've been able to get them comfortable with what our model is, how it was developed, any kind of nuances or quirks to it. And they've been also to give us feedback on what they'd want out of the model and the products that they'd want to look at for it. So for instance, they've had questions about how much variance the model's explained, and also how much of the skill of the forecast is coming from different components in terms of ENSO and MJO and trend. So these are things that we've been able to consider now and start looking at to further refine our product and get this back to the forecasters to help them make informed decisions in development of their forecasts. Our statistical tool was the first model, tool to go into operations to support the experimental week 3-4 forecast. More recently, we have a constructed analog tool developed off the 200 millibar stream function, which still has some kinks to be worked out. but which should be strongly considered in the forecasting process soon. On top of this, we have a number of other statistical models that don't really forecast for North America, but instead give us an idea of the predictions for things like the MJO, like the coupled linear inverse model shown here at the right, dynamical and statistical ENSO models, things like that. And on top of that, in making our forecasts, we also look at a number of observations. Obviously, what's going on with our ENSO and MJO base state. Like at top right here shown is just the CPC's MJO index. This is velocity potential with time increasing along the y-axis, and then the x-axis is longitude here. So you can see we've been in just this ENSO base state with enhanced convection from 140 eastward since about July. So we haven't really had much of an MJO signal to help our ENSO and MJO phase model. So it's just been ENSO and trend for the forecaster since we went live with the forecast here. On top of this, we've been looking some at sea ice, especially in relation to the north slope of Alaska and its impact there on temperatures. We're looking some at soil moisture for influences on warm seas and precipitation and temperature. Also tropical cyclones for any influences on precipitation at the longer ranges, or also anything in relation to recurving tropical cyclones in the Pacific undergoing extratropical transition and amplifying the flow over the North American region here. So here's a sample of the forecast products which Nat showed earlier. Again, this is two-class, temperatures on the left, precipitations on the right. Red regions correspond to above normal temperature, blue below normal temperature, and green and brown being above and below normal precipitation corresponding on the right. And I did pull a snippet here of the forecast discussion. This isn't the most recent. This is from a week ago. But here the forecaster emphasized that the subseasonal ENSO footprint, aka the ENSO and MJO tool that we looked at, because MJO is not active right now. So we're just looking at ENSO. It was strongly utilized by the forecasting team, and along with the dynamical consensus, led to a more confident precipitation outlook relative to temperature, which is reflected in this above normal 60 percentile region here across the southwest. There's only a little bit of it up here in Alaska, and generally less coverage here in temperature than precipitation. So our tool has undergone successful R2O here at CPC and seems to be really appreciated and welcomed by the CPC forecasting team. So just real quick in terms of conclusions, this simple empirical model was able to develop probabilistic temperature and precip forecasts based on the initial state of MJO and ENSO and trend to yield skillful week 3 and 4 forecasts for North America with various seasons and background states in terms of the climate. As I said, this was able to undergo R2O and be available to the forecasting team throughout the dry run process here at CPC, and has been also in use as the forecast went live as of last month. And also key here for us on the research team was the ability of 2 of us to participate in the week 3-4 forecasting process has helped us to get feedback from the forecasting team to drive further research avenues and have that O2R kind of feedback going both ways to help us develop the tool further to support our operations here at CPC. So that's all I have. Pending any time, I'm sure Nat and I'd be happy to answer any questions.
Great, Dan and Nat, thanks so much. Now that I think I'm not on mute anymore, are there any quick questions from anybody for our last talk in the room? And online, you can virtually raise your hand. I don't see anybody's hand raised. Okay, so in the interest of time, we will move on to our last talk of the day. And this presentation will be given by Rachel Hogan-Carr, and she's the Executive Director of the Nurture Nature Center in Easton, Pennsylvania. And today, the project she'll be discussing today was first supported by OWAC in 2012. As part of a set of projects that look at decision-making during extreme weather events, and then it was followed up by a second study looking at the use of emergency briefings in coastal flooding flood scenarios. And so these studies together have opened an opportunity for the Weather Service to receive detailed customer feedback about how their products are used and decision-making, and have resulted in product revisions and planned products and planned and ongoing product revisions. So Rachel, I will now transfer control to you.
Can you hear me, Heather?
I can hear you, yes.
Okay, great.
Okay, so you should have control, and if you just share your desktop, you can begin. Go to the WebEx browser and the Quick Start tab. Great.
Okay, there we go.
And you just put on full
and
screen.
From beginning, got it. Working?
Great.
Okay, super. Hi, everybody. Heather introduced me. I am the Executive Director of Nurture Nature Center. The topic today is the results and findings and then the transitioning into operations of the findings of the social science research study that we conducted beginning in 2012. The project was titled Flood Risk and Uncertainty, Assessing the National Weather Service's Flood Forecast and Warning Tools. For those of you who may be unfamiliar with Nurture Nature Center, we are a nonprofit organization in Easton, Pennsylvania, with a focus on flood risk issues. We were formed in 2007 after some very heavy flooding in the area where we are in the Delaware River Basin, and since then have been doing a number of projects with National Weather Service and NOAA and other federal, state, and local agencies to educate the public about flooding. One of our early projects was in the Delaware River Basin, known as Focus on Floods. And at the bottom of the screen here, you see some samples of some of the outreach pieces that we did there for that project, which you may have seen previously. And that project really focused on on getting the public to increase their use of the Advanced Hydrologic Prediction Service flood alerts. So that was the method, that was the approach behind that campaign. And from that, we learned a lot about how people rely on the Advanced Hydrologic Prediction Service products, and particularly the hydrograph. And this study was born back then. And the way Nurture Nature Center has conducted its work over the years is to be something of a mediator between public audiences and expert audiences. So you see that graphic there where you have us in the middle. And we've done a lot of work outreach on the ground with public audiences who tell us what information they need, what they wish they had access to, and we're able to relay that back to the science and regulatory and policy experts and the National Weather Service and NOAA staff. And vice versa, we're able to work closely with those agencies and organizations and find out the information that they wish the public could understand and act upon appropriately, and we're able to bring that information back to the public in digestible ways that the public can understand. And that's sort of the role that we have played. And then in 2012, we took that role a little bit further and undertook a social science research study. It was one of 4 projects awarded by the Office of Weather and Air Quality in the Oceanic and Atmospheric Research Division. And these 4 projects were designed to look at decision-making during extreme weather events. And they are part of the larger NOAA Weather Ready Nation initiative. And our partners were, as listed here, East Carolina University, and specifically Dr. Burl Montz, who is a noted hazards researcher there. And then we worked with the River Forecast Center, the Middle Atlantic River Forecast Center, and the forecast offices in Mount Holly, New Jersey, and Binghamton, New York, and also with our research corporation, RMC, which has been working with us over the course of many years to help us gather our findings and build a consistent product over the years. And so the issue that we've been looking at here is specifically the fact that the Weather Service tools offer tremendous amounts of timely and accurate data, and still people often don't respond to take protective actions for their life and property. And Gary Zatkowski, who's the meteorologist in charge of the Mount Holly WFO, and we've worked with him closely. He's on a video. This is a still from that video on our website where he's explaining that in his career he's seen major technological advances by the weather forecast in the weather forecast that allow for much more accurate forecasts. But what's needed now additionally is to go the next mile, to use social science to package and communicate that weather warning information so people understand it and take the right action with the time they're given. And that's the heart of this project. So our research questions were to ask, how do people living in the Delaware River Basin understand and use National Weather Service products and services in understanding their flood risk? And what improvements could be made to them so that they work better in 2 ways that I think are important. There's simply so that they're more easily understood and so that people understand exactly what the products are telling them. But then there's also the question of how can we modify them so that they're more likely to motivate people to take protective actions. And that's what we were looking at, specifically with these tools, with the Advanced Hydrologic Prediction Service hydrograph and the flood inundation mapping, also the flood forecast watches and warnings, and specifically the MMEFS ensemble forecast system, which demonstrates uncertainty in flood forecasts. And I'll tell you a little bit about each of those. We did the study through a combination of focus groups and surveys. We did 2 rounds of focus groups. Our test communities were eastern Pennsylvania, where we are, a highly riverine, flood-prone urban community, and downriver a bit on the Delaware, Lambertville, New Jersey, which is much more rural in character, much smaller population, different demographics. And so we tested in these 2 different heavily flood-prone communities. And we brought together groups of residents and exposed them to an extreme flood scenario, a 7-day flood scenario. And we gathered feedback from them about how they use these products. We then went back and modified the products, made visual and text and other revisions to the products, and came back and retested with an additional 4 focus groups and included surveys in each of those. The flood scenario, as you can see here, was based on a hurricane, a simulated East Coast hurricane, and our Weather Service forecast partners called it Hurricane Rachel after me. So this was a 7-day hurricane that went up the East Coast, and we went over a 7-day timeline and showed them day by day the various products that the National Weather Service would issue during an event such as this. This was, in fact, based on the flood of record in the Delaware River Basin in 1955. The participants didn't know that. They didn't understand that this was going to result in the same rainfall that had already happened in the area. But indeed, that's what it was, although it was a hypothetical scenario. And over the course of the 7 days, we showed them hurricane cones, hydrographs, significant river flood outlooks, quantitative precipitation forecasts, watches and warnings, and again, the MMEFS ensemble forecasts that show an uncertainty in the range of possible forecasts. And for about 2 hours during each of these focus groups, we had about 15 participants per session, and we spent 2 hours with them day by day presenting these products and asking their feedback. And they gave us feedback about the timing of the products. So when would they use this product? Had they seen it in the past? At what timeline in the impending event is it helpful? Also, graphic design and visual clarity, and this is where a majority of the effort was made in this project. What visually about this project works for you to help you understand? What is confusing about this product? We asked people to try to tell us in many of the cases, what is this product telling you, and have them convey back what they thought the product was intending to convey. And we were able to gather a lot of information from people that way about how they were using the products. We also asked them about the ways that these products motivated action. So after we show it to you, what would you do next? What's your next step? Once you see this, what do you do? Do you call a friend? Do you go consult another product, et cetera? And also importantly, we talked about how they share the information with others. That was a key piece we wanted to light on, is how people take this information and share it in their social and family and community networks. The findings are that river levels matter. I mean, one of the pieces that really stood out from these focus groups is that people rely heavily on the hydrograph. It was easily the highest ranked product in the focus groups and surveys, and you can see some examples on the left-hand side of things that people had to say about it. It's very clear. It's easy to read. It's useful. Some people called it their Bible, referred to it as that they're in love with this product, that they never leave it, that it's always on their screen. So to flood-prone communities that we were working with, clearly this one was a critical tool. That said, they weren't always interpreting it correctly. They were making false assumptions about certain things. They were not perfectly making taking the right information from it. And so we were still able to go back and improve this product. We do make a suggestion that every other flood product, however, link to the hydrograph because of its prevalence. And when we said to people, when we showed them other of the flood products, when you look at this, what do you do? And they'd say, I'll go check the hydrograph next. So it becomes a key reference point. Another key finding was to use color and to use it carefully. So here you're looking at a quantitative precipitation forecast, and this is one where people really responded strongly to the use of very dynamic color in this product. And so I'm showing it as an example there. There were also cases where the use of color was very confusing to people. In the inundation maps, people were confused by the light and dark shades of blue water that were intended to represent depth, but they misinterpreted them in very interesting ways. There's a flood outlook product I'm going to show you in a minute where the use of shading and patterning and color in that product was very confusing to people and caused them to reject the product almost completely. Then, of course, there's the case where there is no color. People want color and respond to it. It helps them to prioritize risk, to identify themselves. And so in the products, the flood watches and warnings, as they're currently issued, are obviously all black and white text-based. The lack of color and the lack of font variation in those was a complaint from people. So we were able to take feedback about the use of color and patterning into our revisions as well. Here is that significant river flood outlook I mentioned. This gives the first glance, really, of an area that may be under risk of flooding, which is something that participants indicated that they would like to have. Yet when they were shown this graphic, they rejected it almost entirely out of hand because the use of patterning was very confusing to them. They could not find themselves on the map very well. They didn't understand where the black delineation was or what the orange delineation was. If there was a sudden wall where it was no longer going to rain, they couldn't understand what was happening here in this product very well. If you look at the little inlet areas and along the coast, you can see that it turns dark orange. They were seeing that as an indication, according to the legend, that significant river flooding was occurring or is imminent. So they thought that there was coastal flooding perhaps happening. In fact, it's just the intensity of the outline on the out of the product. This product doesn't even show coastal flooding. So there were serious problems with the way that color was translated in this product. One of the key things we did with this project was the uncertainty messages, and the MMEFS graphics have been designed for a more professional user, for emergency managers and water resource professionals and others who may need more detailed information about the risk of certain events occurring. And the question was, would these have any utility for residential users? And so that's what we were trying to test out. And the bottom three images are representations as they were shown to the participants in the focus groups. And I can say with some confidence that nobody extracted any meaningful information from any of them. And there were multiple reasons for this. There were graphic design problems. There were problems with the titles. It's maybe hard to see, but, the titles are GEFS-based stage simulation traces, simulations, probability of exceedance plot, concepts that were not very helpful or familiar to the end user. And so they found these very problematic. But once they understood what they were trying to convey, many users said, well, yes, that information could, in fact, be helpful, but I would need it presented much differently in order to be able to extract that information. So after the first round of focus groups in both Easton and Lambertville, we went back and did revisions, working with our Weather Forecast Office and River Forecast Center partners to make sure that those changes would be viable and workable within current NWS technology. We were not trying to create things that would create extreme expense, but rather trying to make adjustments to current technology and capabilities. And I think we were pretty successful in that. On the left-hand side, you see the current hydrograph as it is, and on the right is a draft mocked-up hydrograph, which makes some significant changes. One of the changes that it makes is to shade the difference between the observed and forecast areas in the hydrograph set differently, so you can more easily and immediately see that one section is for observed and one is forecast. This, we noted, was missed during the original sessions. It also gives a legend. In many of the products that we looked at, multiple of the products, the use of a clear legend was requested over and over. People wanted to understand what the various terms and colors were indicating. And so that legend bar that you see there tries to spell out exactly what those terms are. Also, in many of the products, we reoriented the product at the top with a consistent framework. We took the watermark that says NOAA on the back of the hydrograph and put it up in the upper right-hand corner, oriented the user to the location that they were looking at so that they could quickly identify which region was being covered. You see where it says stream gauge, arrow, Delaware River at Easton. We changed the title to Observed and Forecast River Levels because the previous title wasn't giving people information that was helpful. And we also added an orange bar there that says Prepare Now, Flooding is Possible in the Vicinity of the Stream Gauge. Click for details. We propose that there be some kind of an optional bar there if there is a flood watch or warning in effect that would take people directly to that watch or warning. And if it's a watch, it would be in the Prepare Now orange category. If there were a warning in effect, we would turn that bar red, and it could link directly to the flood warning. So again, getting at this interoperability between the products and giving people easy information that they need. We also, on this one, made some changes to the time schedule. So we took away the universal time up at the top of the product because that was creating visual clutter that wasn't very helpful to these audiences that we were looking at. And the next one is a draft mocked-up uncertainty graphic. This is one of the MMEFS. You can see on the left-hand side the original version and on the right-hand side the mocked-up version. We went through many iterations looking at the various ways that we could represent this information. This is what was ultimately presented to the public audiences who responded much more favorably to this. The dialogue about this product was much richer than it was during the first one. It was still difficult for them. They still had to work to achieve some understanding and information, but they were able to, and they were able to begin the conversation and understand where they were, what they were supposed to be getting out of the product, and had very notable gains. So some of the things that we changed there again is the title, changing it to 7-day river level probabilities, orienting people quickly to where they are. And then a note in blue there. And in many of these products, we've tried to create a place where a forecaster might be able to summarize, call out, and prioritize some of the most important information. We recognize that a lot of these products are automated, but clearly there's a need sometimes in these products for somebody to call out and help the user to identify the important information. If these are going to be presented to public audiences, this is one of those products that needs that bit of translation. And so those sentences explain briefly the information that's presented graphically, and for those more advanced users, they can study the level of detail in there. And then, of course, at the bottom, you see a new legend that incorporates the use of color and a sliding color chart there to indicate certainty from levels of less certain to more certain, and a legend that explains what each of those mean. So you're getting significantly more direction on this product on the revised version than on the original version, and subsequently better outcome from the public. And then this is the last one I'll show right now. You can see the river flood outlook as it was revamped. We changed the colors and the patterning, again added a legend to explain what the different areas were, what the outlined areas were that we're looking here at the Middle Atlantic River Forecast area. We changed the title of this product again to 5-Day River Flood Outlook. And again, have a red note up at the top. This outlook shows the potential for damaging and dangerous flooding to occur in the Middle Atlantic River Forecast Center during this week. Click here for forecast river levels. So again, that could click back to the Advanced Hydrologic Prediction Service. Clearly, there's a very notable change in the shading and patterning, so people could clearly identify themselves. Also, geographic specificity was really a huge point for so many of these products. Here we have done the simple job of adding some key place names so that people could much more quickly identify where they are on this map. Short of having that information presented to them, people felt that this map wasn't telling them anything. In fact, it was giving them information that they really needed, which was an early heads up for the flood potential, but they were missing it. I wanted to also note that we also took away the word significant in most cases and replaced it with damaging. And we aren't the first social science research study to suggest or find that the word significant is not very helpful to people. It's very widely used but doesn't have any parameters. Damaging we proposed because it at least indicates impacts and is consistent with the impact-based warning system that the Weather Service is implementing. Significant, we actually had a participant who said, my significant may be very different than your significant, and so we echo that. So the project began in 2012. Findings were released in 2015, late 2000. I began presenting about them in 2014. The final report was issued early 2015, and the transition to operations is moving rather quickly. MMEFS is a regional product, and so a team including all 4 of the RFCs in the region incorporated these findings into a new design for the products. So they've taken our recommendations, have redesigned the products, and those are going to be launched actually by the end of the year. They presented the findings to their own user groups, customer advisory boards, and other organizations that these river forecast centers work with, and to get additional feedback. We were looking at residential users, so they wanted to test and make sure that the professional users and the water resource managers that use these products are still able to find them useful, and they came up with a very good set of revised products that they will implement by the end of this year, which is pretty exciting. The change process for the AHAPs, hydrograph, and flood inundation, or hydrograph primarily, is different. That's a national product, so that has to happen through a different process, and they've been put into the Weather Service requirements process for consideration and prioritization. So they've been recently put into that queue, and now we will just wait to see what happens next with those. And the significant river flood outlook, again, this is a regional product that we were looking at. However, offices all across the country issue this product, but they do it independently, and then they are mosaic together into a national river flood outlook product, and this is done by a national office. But this study has helped to trigger a reconsideration about how this product is issued generally. And so now there is a team doing a national plan for the generation of SRO that will allow it to be generated on a regional basis and also automatically mosaicked into a national product, and that will incorporate our recommendations. So our recommendations were geared toward the Middle Atlantic River Forecast Center region, but those will be incorporated into the plan that's going to be happening nationally. So we're happy to see that had a larger impact. And we have some websites where you can find more and find our findings is socialscience.focusonfloods.org. There's a research bibliography and some project information, a video. We also have educational materials and our final reports and papers on that website. And then if you link to the coastal.focusonfloods.org, you'll find that we also have completed a similar study for coastal flood forecast and warning products, and that is available there as well. And I'm happy for any questions.
Rachel, thanks so much. That was really interesting. Are there any questions in the room? Okay, and online, I don't see any questions, but okay, and we are running over, so at this point, I think we should wrap up, and I'd like to thank the 4 speakers for really excellent presentations on a variety of R2O, R2A, transition-related projects going on at NOAA, and thank everyone for participating. Our webinar next month is going to be on the nuts and bolts of creating environmental intelligence, and you can stay tuned for the date and set of speakers. Okay, so thanks again for joining.
Thank you.